Hello, my name is Major Jonathan Wright, and today I'll be talking to you about the attitude determination and control subsystems. I'm excited to talk about this topic because I actually studied attitude determination control systems for my PhD at AFIT. Here's a picture of my test platform. We had 6 fans that were used to simulate thrusters, 3 reaction wheels, and 4 control move gyroscopes. Here's a quick overview. We're going to talk about the quick definition of what attitude determination control is. We'll talk about open and closed loop control systems, cover some equations of motion, attitude determination systems, and then attitude control systems. So here are our lesson objectives. Alright, so quick definitions. What are attitude determination and control? So just like in an airplane, attitude describes our orientation. So in an airplane we have roll, pitch, and yaw. And similarly, we describe the attitude of a satellite in slightly different terms, but it's the same thing, attitude it is. So how do we determine it? Well, on my test platform, I can actually just turn around and look at it. But for satellites, we can't always do that. So just like in an airplane, we have sensors and various gauges that we can use to determine our current orientation. And then if we're not looking where we want to look, then we have to control. Maneuvering our satellite's attitude and steering it to look at something else. In an aircraft, you would have rudder, elevators, flaps, and ailerons. But in satellites, we don't have that much air, so we can't use lifting surfaces. Instead, we have to use different techniques. So the first couple of learning objectives have to do with open and closed loop control systems. So let's talk about open and closed loop control systems. So this is an example of a simplified open loop controller, right? So you have a desired output, your controller, your actuator, and then your plant. And the plant is actually kind of the physics of what's going on. And then you have the actual output. So a quick example of an open loop control system is basically a basic controller for a DC motor, right? So let's say we want 5,000 RPMs. The controller would say, hey, we need 5 volts of power. In this case, the actuator would be a voltage regulator. It actually generates that 5 volts of power, and then our plant would be a DC motor. And after all of that, our DC motor is spinning at 5,000 RPMs. So this is great in that it is simple, but if anything goes wrong, then we see some adverse effects. So here's an example of the same exact motor with the same exact input, but now we have a disturbance. So our voltage regulator is acting up. It's off by about 2%. As you see, we still input the desired 5,000 RPM. The controller still says we need 5 volts of power, but now our actuator, our voltage regulator, is off by 2%. See, even if everything else is perfect, our output is now off by 2%. So sometimes it's okay and we don't really care about being perfect, and in which case this might be perfectly fine. But if we actually needed that 5,000 RPMs output, we need to find a way to reject that disturbance. And one of the ways we do that is with closed loop control. So closed loop control looks mostly like the open loop controller, right? So you have your desired output, you have your controller, you have your actuator, your plant, and your actual output. But now we're taking that actual output and we're measuring it and we're comparing it to our desired output. So let's do a quick example, right? So we have a DC motor. We desire 5,000 RPMs. We still have the controller that's outputting 5 volts. We still have the actuator that's a bit off by 2%. It's outputting 4.8 volts. So we end up getting 4,900 RPM instead of the desired 5,000 RPM. Well, now we've actually added a sensor, in this case a shaft encoder, and it feeds that 4,900 back in. Well, now the controller says, okay, I'm off by 100 RPM. I need to increase my voltage by 1/10 of a volt. So it does. So now it's outputting 5.1 volts. The voltage regulator is still off by 2%, right? It doesn't output 5.1 volts. It outputs 4.998 volts. But when it does so, feeds that to the electric motor, we're able to get 4,998 RPM. So we've gone from a 2% error to actually a 0.04% error. And this is just the first loop through. In reality, this would continue to refine that controller voltage until we actually get to that 5,000 RPM. Here's a quick side-by-side comparison. Open loop controllers, they're great in that they're simple. They're not so great in that they can't reject disturbances. The closed loop controller, it's a little more complicated, has a little more components, right? We actually need those sensors. It's a little more, sometimes it can fail if the sensor goes bad, and we have some various complications. So on the whole, it's more complicated, but as a pro, it's actually able to reject a lot of disturbances. So the next two, similar to the first two, are they're difficult to separate, and these are kind of where the math comes into the lesson. So we need to calculate the target distance, spacecraft altitude, when given attitude pointing error and/or attitude pointing accuracy for a given situation, and then we also need to describe the physics principles that govern attitude dynamics. So since this is the math part, let's pull up the equation sheet. So this is page 2 of the equation sheet, and as you see, we've put the controls equations underneath the heading control. Easy enough. And if I had to break these equations into those two learning objectives, the one on the left would be calculate pointing accuracy, and then the two on the right would pertain to describing the physics principles. So pointing stability, what is it? What's the equation? How do we calculate it? All right. The big thing to remember is we can ask you this question in 3 different ways, right? There are 3 terms that are in the equation, and we can give you any 2 and ask for the other 3. It only shows up in one form on your equation sheet, and that is D is equal to H psi. So D is the pointing stability distance on the surface. All right, so if we look over here, it's kind of how large of a distance is that uncertainty corresponding to on the surface. Psi is kind of the uncertainty angle, and that's at the spacecraft level. And then H is just the height of the spacecraft. It's important to note that this is height, right? This isn't semi-major axis, this isn't radial distance, this is height. So if you're given A or if you're given R, you will need to subtract the surface of the Earth, or the radius of the Earth. So D is the pointing stability distance on the surface. H is the satellite's height above the ground, and it's important that these are in the same units. All right, it doesn't matter if they're both in furlongs or if they're both in parsecs, right? They just have to be in the same units. Psi is the pointing stability angle, and that has to be in radians. Because that is an angle that shows up by itself, not inside a trigonometric function, we can't rely on that trigonometric function to correct for our units. All right, so it has to be in radians. All right, so D and H, distances in the same units, psi and angle always in radians. We can give you any 2 and you can solve for the third, but that equation only shows up in one form on the equation sheet. And this you will have to compute. So be prepared for no matter what 2 values we give you, you will have to compute the third. Now we are on to the describe portion, right? So these are the equations that we're talking about. And for this, I would like to use a basic diagram. Here's a satellite with a sensor and here's a target, right? So we want to get the satellite to be oriented so that it is looking at the target, right? So there's 2 ways to do this. The first is to apply an external torque. So right now, if I look at my camera and I wanted to change where I was looking at, I would reach over, I would apply a torque, and it would turn, right? Similar principle to satellites. So what would this look like on orbit, since we can't really go up and grab satellites, at least not very frequently. All right, so start here. We have our satellite with our sensor and our target, and the satellite is not looking at the target. We apply an external torque of some sort. All right, in this case, this looks a lot like thrusters. All right, we would fire them in pairs so that we're not increasing the velocity or anything. We're kind of just inducing a torque. Once we induce that torque, we have an angular velocity, and the satellite starts to rotate. Once the satellite is pointed at the target, we're at the correct orientation, but we're not actually in a position where we can continue to looking at the target because we still have that angular velocity. So we apply a counter torque, and at the end of the day, our satellite is looking at the target and has 0 angular velocity, so it can continue to look at the target. These are what the equations look like. They look a lot like Newton's second law, right? So it's just standard F equals ma. In this case, you have torque is equal to I, the mass moment of inertia, times the angular acceleration. So I for rotation is similar to m for translation. And remember, you just have to be able to describe this, right? So the second way that we can do that is by applying what we call an internal torque, or by exchanging momentum on the spacecraft. All right. So once again, we have our target, our sensor, and our satellite. And this time, we want to have our satellite look at the target, but we're not going to apply an external torque. We're going to apply an internal torque, or a momentum exchange. So we have our reaction wheel. And what we're going to do is we're going to spin our reaction wheel opposite the direction we want to turn. And then the counter torque is going to turn our satellite in the opposite direction. All right, so the action is turning the wheel. The reaction is us looking in the opposite direction. So that looks a little something like this. All right, and then once we are looking in the corrected direction, we just despin the reaction wheel. And now we're in the exact same angular momentum state as previously, only we've rotated, right? Because there is no external torque, h dot is actually 0. All right, and h dot in this case is the sum of the two angular momentums. So that's why we call it a momentum exchange, or a momentum storage, or a momentum transfer, or an internal torque. And basically, this equation starts looking a lot more like Newton's third law, right? Once again, you should be able to describe this, right? We're not going to give you necessarily torques and angular momentums, angular velocities. It's a little deeper than we intend to cover in this course, but you should at least be able to describe. All right, reiterate, calculate, describe. All right, so satellite added determination, right? How do we know that we're looking in the wrong direction if we don't know where we're looking, right? So there are various subsystem or types of components that we can use to do this. And the learning objective is to actually know and be able to identify the various types, the advantages and disadvantages of each. Right? So the first one is the magnetometer. All right, so the Earth is a giant magnet. Right? And similar to how we can use a compass on the surface of the Earth to determine which way we're looking, we can use a compass in space to determine kind of which way we're looking. A couple of advantages, right? It's cheap, right? These things are, in terms of sensors, pretty low cost, pretty low power. One of the disadvantages is that the further you get away from the magnetic source, you have that decay with the square of the distance, right? So this really only works for low Earth orbits. It's fairly orbit dependent, and then it's fairly low accuracy. And if you think about it, it'll tell you the direction of the magnetic field, but it won't tell you your orientation about that direction. So even though we can get fairly decent information about two of our three-dimensional space, it's still only a partial solution. We will need something else to augment that solution, right? The second is a star tracker. Now, this is kind of like the Rolls-Royce of attitude determination. And basically, you have a camera and kind of multiple cameras and a lot of times, and you're looking at pictures of the sky. Now, from that picture of the sky, from the orientation of certain stars, from certain constellations, we can actually get a very good estimate of our orientation, right? So the advantage is that it is incredibly accurate. The disadvantage is that it's heavy, complex, and expensive. So you kind of pay for the precision that you're getting. The next is a sun sensor, right? So if we can determine our orientation off of the stars, the sun is a giant star, maybe we can use that. And It's fairly good. It's simple, it's reliable, it's low cost, but there are some disadvantages. The first is bring back the magnetic field reference, right? Just because I know the direction of the sun doesn't mean I know my orientation about that direction, right? So it's still only a partial solution. It's only two pieces of information, and then the other is that it's not always visible, right? So when your satellite is in eclipse, then you're not going to be able to see the sun. You're not going to be able to use it. Also, depending on where your sensor is, you might have to actually slew to see the sun, and you may not be able to determine your attitude while also accomplishing the mission simultaneously. And the next is the Earth horizon sensor. All right, so similarly, we can get a decent idea of our orientation based off of where the horizon is. That's similar to an artificial horizon in an aircraft. And one of the downsides of this is that it's orbit dependent. And once again, you're back to scanning for the solution as opposed to it kind of just being there. And for what it gets you, it's relatively expensive. So next is differential GPS. And I actually added this picture of Gollum into the slideshow because when I think differential GPS, I think about these motion capture technology. Right? So basically, if I have 2 points and I know where they are relative to one another, then I can draw a line between the two of them and get an attitude. Right? And that's pretty much what differential GPS is doing. If you have a fairly large spacecraft and you have multiple GPS sensors on it, you can plot where those GPS sensors are in space and then kind of draw lines between them to figure out your orientation. So here's the typical sensor accuracy. And if you'll notice, differential GPS just has a question mark. That's because differential GPS is using a position estimate to get an attitude estimate. So there's really not a one-to-one correlation. It really depends on the size of your spacecraft and the precision of the GPS when you're using it. The magnetic field, you're probably only good to about a degree. The Earth horizon sensor, about 1/10 of that. The sun sensor, 1/10 of that, but then the star sensor, 1/10 of that. All right, so you can get more and more precise, but you can almost look at that as an increase in cost as well, except for the differential GPS. If we actually plotted it in terms of precision, differential GPS would probably be considerably higher than star sensor. Gyroscope. So this is an honorable mention. This actually doesn't determine your attitude per se. It determines the difference in your current attitude from a previous attitude. So remember how we had to scan for, say, the horizon and then possibly even the sun sensor? If we're scanning for the horizon, then we can kind of get a baseline and establish the baseline, and then we can go back to doing the mission. Well, between scans, the gyroscope is what we do use in order to determine our current attitude. So it works similar to an accelerometer. Right, so if you have accelerometer data, you can integrate that to get velocity estimate. If you integrate that again, you can get position estimate. Now, because you are integrating noisy data, then you get introduce errors which don't necessarily go away. Right? So you need to continuously re-zero your errors. You need to go back occasionally and establish where you actually are so you can zero out those errors. Fortunately, the gyroscope isn't measuring acceleration, it's measuring velocity. So we don't have to integrate it twice, we only have to integrate it once, which is nice. And it allows us to keep the errors a little bit smaller. So now, highlighted the same learning objective because there's kind of two hidden in there. We need to know the different sensors. We also need to know the different types of actuators, and then be able to determine the difference between an active actuator and a passive actuator. All right, so active, I like to use the description that an active is something that we are controlling, turning on and off, and kind of more actively controlling. All right. Passive, we might turn on, but then it's more fire and forget. It kind of does its own thing without continual monitoring. So an example of an active control system is thrusters. Right? They are continuously firing as needed. And even though we may not have a human in the loop telling them to fire, like the Voyager, for example, it's still being actively controlled and it's still being told to fire actively. Right? It needs to be turned on and off. Magnetic torquer. All right, so we said that the Earth is a magnetic field. We can actually use that magnetic field to apply a torque on our spacecraft if we actually take little electromagnets and turn them on and off. As we turn these magnets on and off, then we can apply an external torque to our spacecraft. All right, so those two were external torque devices. The next, we're actually going to go into momentum exchange devices and whatnot. So the first is momentum wheel. Basically, it can absorb the angular momentum induced by disturbance torques and help your satellite stay positioned where it's at. It can also be used to spin up and spin stabilize the spacecraft without necessarily spinning the spacecraft. The next is the reaction wheel. And I don't know if I can get this to play, but unfortunately I can't. The reaction wheel, basically, we've talked about the example earlier. If we want the spacecraft to look into a different direction, we spin the reaction wheel in the opposite direction. That momentum is exchanged, and then now the reaction wheel spinning this direction, the satellite's spinning that direction, and once the satellite's looking where it wants to, then we despin the reaction wheel and go back to that zero angular velocity state. Right. Reaction wheels are great because they're actually pretty precise. Right? Control moment gyroscopes. Now, this is kind of my bread and butter for my research topic, but control moment gyroscopes, they're giant flywheels, right? And the giant flywheels store angular momentum. And they're gimbaled, and it allows us to change the direction of that angular momentum. Now remember, angular momentum of the spacecraft doesn't change. So if the angular momentum of the flywheel is changing by pointing from this direction and now pointing in this direction, we've just imparted a tremendous amount of torque on the spacecraft. So these are typically fairly large. Pro is that they produce a tremendous amount of torque. One of the cons is that they're complex. They're kind of expensive. They scale up very well, which is a good thing, right? They can produce a tremendous amount of torque as they get larger and larger, but they don't scale down very well. So you're not going to see these on small satellites. So here's a quick little picture on how CMGs work. So we've got our satellite again, and now we have two flywheels on gimbals, so they can rotate. So they can rotate in this direction or this direction. All right. So here's our little gimbal. So what happens as this flywheel rotates this direction and this flywheel rotates in this direction? We'll see what happens to the spacecraft angular momentum. All right. Because the sum of these three angular momentums have to remain the same, then the spacecraft just took on a very large angular momentum in the opposite direction. So, like I said, they produce a tremendous amount of torque. They scale up very well, but they are large, they are heavy, they are complex. And even though they are fairly precise, they're not super precise. So in terms of large spacecraft, good for the world view, not necessarily good for the Hubble. All right. So now we're talking about passive control. Now, I think this confuses some people because some of these actually have to be turned on, but they're not turned on and off in such a way as the others. It's kind of, if we even do have to turn it on, it's kind of fire and forget. The first example is gravity gradient. All right, so we have two masses and a long boom, and the gravity gets weaker as we get higher up. All right, so gravity is going to be pulling harder on this bottom one, and as a result, it's going to put this boom in a tension. Right, it's going to cause that boom to behave similarly to a pendulum. And when that happens, as energy slowly dissipates through time, it's going to go to a minimum energy state, and it's going to look like a pendulum that's no longer swinging, where the pendulum is at the very, very bottom of that arc. This is something that we incorporate into the design. We never have to turn on. We can't turn it off, and it just works. All right. Next is spin stabilization. So brought back that gyroscope, but similarly to how we spin stabilize a ball. All right. If you spin up something and you give it a large angular momentum, it's going to be much better prepared to reject small disturbance torques because that large angular momentum is going to be considerably larger than the small angular momentum that it's going to pick up with those disturbance torques. It's going to allow it to stay in a preferred orientation. Similar to how the football remains pointed in the right direction when it's spun as it's released. Right? It's same type of idea, just applied to large objects in space. So let's talk about various precisions, right? So gravity gradient, you're not going to get super precise with that, all right? But it is nice. It's passive. We don't even have to turn it on. It just works. The physics of the situation say that it's going to work. Magnetic, right? So remember magnetic, we had to turn those on and off. Basically, those little electromagnets allowed us to interact with the Earth's magnetic field. Not fantastic, right? You're only going to get about 1 degree, which kind of makes sense because you're only able to get about that good with the magnetometer anyway. There's just too many natural variances in the Earth's magnetic field, too many things to kind of throw off that estimate, which is essentially a closed loop system anyway, right? Spin stabilization. If you're accurate when you spin up, then you're gonna mostly maintain that accuracy, right? The small disturbance torques may throw you off by 1/10 of a degree here and there, but as a general rule, you're going to be able to hold that precision you have when you fire it up the first time. When I say fire it up, that's actually because you typically use thrusters to get that spin stabilization. So I'm not surprised to see thrusters as on the same order of precision as spin stabilization. Control moment gyroscopes, right? The benefits, they scale up very well, tremendous amount of torque, tremendous amount of angular momentum, but they're not tremendously precise. All right, it's still a lot better than a lot of the other options, but if you have very, very precise requirements, then you're going to want to go either to reaction wheels only, or if you have a giant satellite that you need a tremendous amount of torque and precision, then you probably end up having to do CMGs with a reaction wheel as well, which some spacecraft do. All right, since I've been talking for over 30 minutes, loop back to the front, metaphorically speaking, and talk about the controllers, right? We've got open loop, we've got closed loop. Open loop's great. It's simple, but it can't reject disturbances. Closed loop, a little more complicated, but it is able to reject those disturbances. For the learning objectives, you should know the closed loop, also know the open loop, but if you're familiar enough with the closed loop, then you should be able to fill out the open loop because it's pretty much the same thing. And that's the end. Thank you for your time.
All right, you guys, let's just really quickly talk about one of the quickest, easiest problems that you're going to get in this class, which is awesome. Let's get some free points together. Free points. Free points. I don't hear anyone cheering. Okay, that's all right. Okay, so on the equation sheet, if your equation sheet looks like mine, which it should, we're going to look at the, stop flipping the page over, at the control section, which is on the back page, on the left side, in the middle-ish. And I'm going to do last year's homework problem. Again, there's conceptual stuff at the bottom. You guys can look that up, and I want you to, if the homework looks like this. So, okay, number 1 says, the WorldView 3 satellite is a remote sensing satellite that provides imagery used in Google Earth. That's actually true. I don't know if you guys knew that. It's a company called Digital Globe that, or from whom Google buys a ton of imagery. And so, kind of interesting, if you go into Google Earth, look up your house, it'll say when the image of that was taken, and sometimes it'll say the source, sometimes it's a government source, sometimes it's, Digital Globe, sometimes they'll tell you the satellite it was taken from, like WorldView, which is kind of cool. So anyway, let's assume what the problem says, that you have WorldView 3, and he needs a pointing stability of 15 meters, and that's how we measure that. It says if the WorldView 3 satellite is in a circular orbit, yay, with a semi-major axis of 6878 kilometers, what pointing accuracy, right, so there's stability, accuracy is a question mark, what accuracy must we have? Provide our answer in degrees. That's actually going to make a little bit of a difference here in a second. Okay, here's the equation that we use. Oop. Yeah, D. D equals H psi. That's what we call that. Looks like a little pitchfork. D equals H psi. So first of all, let's see. So basically, what you want to do here is first of all, H is height. They gave us the semi-major axis. They did not give us the height. So we need the height. The height is the difference between the image and the camera. Or put another way, the distance between the photograph taking camera on the satellite, which is WorldView 3, and then the distance between that satellite and the thing it's taking a picture of. So if you guys remember, well, yeah, just the thing it's taking a picture of. So the semi-major axis of the satellite is 6878. That means that from the center of the Earth, center of the Earth, here's the surface of the Earth, right? There's trees and mountains and stuff. And here's WorldView. The distance between it and the Earth that it's imaging is height. So semi-major axis is the distance between the satellite and the center of the Earth, right? Well, in this case, because it's a circular orbit. So anyway, we're going to subtract out the radius of the Earth, 6378.137, to get the height. Let's do a little plug and a little chug. It's me 499.863, almost 500 meters even, which is kind of cool. 500 kilometers rather, even, sorry. Now, this is an important note. All distance units need to be the same. What I mean by that is our pointing stability is given to us in units of meters. So I'm going to convert this to meters. Okay. So what we're looking for is this pointing accuracy, which is psi. Let's real quickly solve for psi. D over H. Okay, so what's H? Well, what this equals is the pointing stability, which is 15 meters, over the height, or the distance of the satellite, but this is the distance between the satellite and the ground, which is this huge number of meters, right? 499,863 meters. Okay, and so when we do that, we do 15 divided by, no, 3. That gives us 3 times 10 to the negative 5th radians. Now remember radians, I wrote it here, radians. This equation spits out radians when the meters and the meters are the same, they're the same distance unit, it spits out radians. But the problem wants it in degrees. So let's convert to degrees, we can do this. I heard tell there's pi radians in every 180 degrees. So why don't we multiply by that? I get 0.0017 degrees. So the pointing system, the stability system, if you will, the attitude determination control subsystem, with all of its wheels, its thrusters, and everything, has to keep a very precise pointing accuracy of 0.00172 degrees. That's a tiny fraction of a degree. Or else it's going to produce images that don't look clear, they're not looking at the right thing. And that's why we do this kind of a calculus to kind of figure all this out. Because that goes into building how great the camera needs to be and all the physics behind that. So Anyway, that's the quick math that goes behind this part of Astro 310. As always, it's been great. I'll see you guys next time.